buffer solutions and how buffer solutions resist changes in pH. A buffer solution resists changes in pH when small amounts of acid or alkali are added. In a bit more detail, a buffer is a solution which resists changes in pH when a small amount of a strong acid or base is added, provided that the amount is less than that of either component in the buffer. A buffer can be an acidic buffer, a weak acid, together with a salt from that acid containing the conjugate base. Or, for an alkali buffer, a weak alkali, together with a salt from that alkali containing the conjugate acid. The pH of a buffer solution depends on two things: the pKa or pKb, in other words, the strength of its acid or base, and the ratio of the concentration of acid or base to the concentration of the conjugate base or the conjugate acid. For an acidic buffer, the weak acid, Ha, is partly dissociated. Its fully ionized salt completely soluble. The weak acid is barely dissociated. It provides a reservoir of Ha. The salt is completely dissociated. It provides a reservoir of A-. So in the acidic buffer, we've got surplus undissociated acid Ha and surplus A-, the conjugate base. Addition of acid to the buffer. H+ increases due to the addition of acid. Equilibrium for the weak acid shifts to the left, removing the extra H+. The A- ions necessary are supplied by salt. Addition of alkali to the buffer. Concentration of hydrogen ions now decreases as the alkali removes the hydrogen ions. Equilibrium for the weak acid shifts to the right, restoring H+. In an acidic buffer, the salt supplies the conjugate base in excess to maintain the pH when an acid is added. The weak acid itself produces the extra hydrogen ions to react with hydroxide ions when an alkali is added. The acid needs to be weak so that there are a large number of non-ionized, non-dissociated molecules which can act as a supply of hydrogen ions to react with added hydroxide ions. A small reduction barely affects pH, which would dramatically change if acid or alkali was added. For an alkali buffer, this time we have a weak alkali which will dissociate slightly. It provides OH- ions which will determine the pH of the buffer. There's a reservoir of MOH. Here's my weak alkali, only slightly dissociated, providing that reservoir of MOH molecules. That reservoir can dissociate to restore OH- ions if some is removed by the addition of a small amount of acid. The salt, Ma, is completely dissociated. It provides a reservoir of A- ions if acid is added. There is my salt completely soluble, breaking up to provide a large supply of M+, the conjugate acid. Addition of acid to the buffer. OH- ion concentration decreases as hydrogen ions from the acid react with it. The equilibrium for MOH shifts to the right to restore the OH- ion concentration. More of the alkali ionizes to allow this to happen. Due to the increased ionization, OH- ion concentration is brought back up again to the level it was before the acid addition. Here is my mixture again. My addition of alkali this time. Equilibrium for MOH shifts to the left. The extra OH- ions are mopped up by M+ ions supplied by the salt. The OH- ion concentration is brought back down to the level it was before the addition of alkali. Concentration of MOH increases as equilibrium is shifted to the left. Concentration of M+ decreases as it's being used up to react with excess hydroxide ions. In an alkali buffer, the salt supplies the conjugate acid in excess to maintain the pH when an alkali is added. As the conjugate acid combines with the extra hydroxide ions, the alkali itself produces extra hydroxide ions to mop up any hydrogen ions that were added when an acid is added. pH of an acidic buffer solution. So I've got my general equation for the dissociation of a weak acid. Very, very slightly dissociated. And I've got my equation for the complete breakup of the salt into its ions. My expression for Ka for a generalized weak acid. Two very important and very good assumptions. Concentration of A- at equilibrium is assumed to be the original concentration of the salt. All of my A- ions are assumed to come from the salt. The salt is completely dissociated and very few A- ions come from the weak acid. Second assumption. Concentration of the weak acid at equilibrium is taken to be the original concentration of the acid. Very little acid is dissociated. It's weak. Now, an example question based on a past paper question I've seen before. A buffer is made by dissolving, and I'm given the concentration of the salt, potassium ethanoate, and I'm given the concentration of the weak acid, ethanoic acid. Ka for the acid as given. Question, what is the pH of the buffer? Okay, so here's my equation for the very partial ionization of the weak acid. Here's my Ka expression for the weak acid. Now I'm substituting the value for the ethanoate ions CH3COO- as being 0.3. I'm substituting my value for the concentration of the acid at equilibrium as being 0.6. Now I have an equation where the only unknown is the concentration of hydrogen ions. It falls out. Hydrogen ion concentration is 2.0 times 10 to the negative 5. From there, pH is negative log of the hydrogen ion concentration, which turns out to be 4.70. pH of an alkali buffer solution, again, based on, I would say, a difficult question I've seen from a few years ago. A buffer contains, and I'm given the concentration of a salt. And I'm given the concentration of a weak base, ammonium hydroxide. What's the pH of the buffer? Given Kb at 298 K. My equation for the complete dissociation of the salt, my equation for the partial dissociation of the weak base. Concentration of NH4OH at equilibrium can be taken as 0.8. Wouldn't have changed much as so little is dissociated. Concentration of my NH4 plus is taken to be 0.2, as negligible amounts come from the weak base. I can now write my expression for Kb based on the partial dissociation as given above. And that is, the value is given as 6.0 times 10 to the negative 5. From here, rearranging to make the concentration of OH minus ions the subject. Substituting in my values gives me an OH minus ion concentration of 2.4 times 10 to the negative 4. I choose to use Kw. Kw is the concentration of OH minus ions multiplied by the concentration of hydrogen ions is 10 to the negative 14. From here, I can calculate the concentration of hydrogen ions, which is 4.2 times 10 to the negative 9, and from there, the pH, 8.4. Finally, the effective dilution of a buffer. The pH of a buffer depends on the ratio, concentration of the weak acid or base, and the concentration of its salt. Both acidic and basic buffers contain a weak acid or base and its ionized salt. Dilution of a buffer dilutes both by the same amount. That's the key. Dilution of a buffer dilutes both by the same amount. And so, dilution of a buffer has no effect on pH. However, it does make equal volumes of the same buffer less able to resist changes in pH when small amounts of acid or alkali are added. The concentrations of the undissociated acid or base and its salt are lowered, and so the reservoirs of the weak acid or base and its salt are lower. That's it. If you found that useful, please hit like, please subscribe to be informed of more content.